Hello, this is the section 4.3 lesson. In chapter 3 we talked about the commutative and associative properties of addition. Well, in this section we're going to talk about the commutative and associative properties of multiplication. The basic idea of these properties is the same for multiplication as it is for addition. The only difference here is that in this section we're going to be using multiplication rather than addition. So our first example here is going to be a very simple example that's going to illustrate the commutative property of multiplication. So here's a question: how many marbles are in the figure below? Well, we could just count the number of marbles and we'd get 15, but let's look at how we could describe this number of marbles using multiplication. Now there's a couple of ways we could look at this. One way is to group our marbles in terms of rows, and so we have 3 rows, and in each row there's 5 marbles, and so grouping them this way, based off our meaning of multiplication, we should have 3 times 5 marbles. Well, let's look at this from a different perspective. Let's group them according to columns like this. So now we have 5 columns, 3 marbles in each column, and so we have 5 times 3. So both of these expressions here, 3 times 5 and 5 times 3, describe the exact same number of marbles. So the point here is that these two expressions should be equal. 3 times 5 should be the same as 5 times 3, based off of our meaning of multiplication. So this example illustrates this commutative property of multiplication, which in general says that a number a times a number b is the same as taking the number b times the number a. And so in other words, we can summarize this by saying that when we do multiplication, the order does not matter. Same basic ideas as with the commutative property of addition, which says that when we do addition, the order doesn't matter. Here we're saying that when we do multiplication, the order does not matter. Now let's talk about area and how multiplication is related to area. And so we're going to start off with a definition here of the area of the square that is 1 inch by 1 inch. And so here's a square that's 1 inch by 1 inch. It may not look exactly to scale, but we'll just pretend this is 1 inch and this is 1 inch. So we're going to define the area of this square to be 1 square inch. So very simple definition. But now let's try to apply this definition to a little bit more complex example. What's the area of this rectangle here that is 2 inches high by 3 inches wide? Now you may say to yourself, well, that's simple. The area is 2 times 3, but why do we multiply 2 by 3 to get the area? What is it about the meaning of multiplication that allows us to calculate area using multiplication? Well, let's make this observation, or this really definition. The area of this rectangle is going to be the number of 1 inch by 1 inch squares inside of the rectangle. Okay? And so we can count the number of squares. Well, there's 1, 2, 3, 4, 5, 6. So the area is going to be 6. But let's look at how we can use multiplication to figure out that area. So let's kind of group these rectangles or these squares like this. Let's make one group there, and another group there, and another group there. Okay. So now the number of rectangles, the total number of rectangles, is going to be the number of groups, which is 3, times the number of rectangles in each group, or the number of squares in each group, which is 2. So 3 times 2, that's going to be my area. So that's why it makes sense to calculate area by multiplying. To find the area, we want the number of squares inside of the rectangle. In order to do that, we can group it like this, where we have 3 groups and 2 squares in each group. So we multiply that to get the total number of squares, which is the area. So this simple example illustrates our definition of the area of a rectangle. The area of the rectangle is the length times the width. and by length will mean the kind of horizontal direction, and then the width will be the vertical direction. And as we'll see, it really doesn't matter which we call the length and which we call the width. So let's illustrate the point that we just made. That doesn't matter what we call the length and what we call the width. Let's find the areas of these two rectangles here. Well, first let's just look at these rectangles geometrically. Here we've got a rectangle that's 3 wide by 2 high, and here this is 2 wide by 3 wide, or 3 high. And so to go from one rectangle to the other, all we did was we took this rectangle and rotated it 90 degrees to get that rectangle, the other rectangle. Well, if we just rotate a rectangle, that's not going to change the area. It may change how we calculate the area, but it's not going to change the actual area itself. So let's use our definition of area to calculate the area of these two rectangles. So this rectangle here is 3 wide by 2 high, so 3 by 2, whereas this rectangle is 2 wide by 3 high. So those two expressions should be equal because they represent the same area. So 3 times 2 is the same as 2 times 3. So this illustrates that if we just switch the numbers around, we should get the same answer. Well, that's just exactly the commutative property of addition, or of multiplication. So again, this example is a way of geometrically illustrating the commutative property of multiplication. We take our square, rotate it 90 degrees, we don't change the area, but we do change how we calculate the area. We just switch the numbers around, but we should get the same answer. That's exactly the commutative property of multiplication. Now let's talk about volume, and we're going to use the idea of volume to illustrate our second property of multiplication, namely the associative property. So like with area, we're going to start off by defining the volume of a really simple shape. So the definition: the volume of a cube that is 1 inch by 1 inch by 1 inch is 1 cubic inch. And so here's a cube that's 1 inch by 1 inch by 1 inch. May not be to scale exactly, but we'll just pretend that all those measurements are 1 inch. So that the volume of that cube is 1 cubic inch. Well, let's apply this definition to a little bit more complex example. What is the volume of this box below? So here we've got this three-dimensional box that is 3 wide, or 3 inches wide by 2 inches deep by 4 inches tall. And so this is very similar to that example of that rectangle that we did earlier. And so to find the volume of this box, we're going to use the same basic idea as what we did to find the area of that rectangle. Namely, we're going to say that the volume of this box is the number of cubes inside the box. Just like before, the area of that rectangle was the number of squares inside of the rectangle. So now we could count the number of cubes in this box. It might be a little difficult because we can't see all of them, but we could count them, and that would give us our our volume. Well, let's look at how we can use multiplication to find that number of cubes inside the box. So let's take our box here and let's break it up or decompose it into several different layers. So we're just going to take this box and break it up. There's the first layer, second, third, and fourth. And so now let's think of each one of these layers as a group of cubes. So we have 4 groups of cubes. Now let's look at each one of those groups and figure out how many cubes are in each one of the groups. So let's take this group down here, for instance. So that group consists of, well, 2 rows and kind of 3 columns of cubes there. So the number of cubes in one of those groups is 2 times 3. So that's so what we have here is 4 groups. each group consists of 2 times 3 cubes. So if we put all this together, the number of cubes is going to equal the number of groups, which is 4, times the number of cubes in each group, which is 2 times 3. And so there we've calculated our number of cubes, which is our volume, using multiplication. So in the end, what we did is we just took the height times the width times the length and multiplied them, and that gave us our volume. So let's use this example to generalize our definition of a volume. So the volume of a box is the height times the length times the width. Now it really doesn't matter which dimension we call the length and which one we call the width, because the commutative property of multiplication is we could switch those around and we're going to get the same thing. So it doesn't matter what dimension we call the length and the width and the height. The point here is that in the end we're going to multiply all three of them, and that's going to give us our volume. So this example and this definition illustrates why we calculate volume by multiplying. Now let's use this same box to illustrate our associative property of multiplication. So to do this, we're going to look at this same box, and we're going to calculate the number of cubes in this box in a couple of different ways. We're going to break it up in two different ways. We're going to break it up like this, and then we're going to break it up like this. And so in this first way of breaking it up, what we have there is 4 groups of cubes, and then in each group we have 2 times 3 number of cubes. Now over here in this in this grouping, what we have there is several different groups. Each group consists of 3 cubes. Now how many groups do we have altogether? Well, these groups are kind of broken up into kind of like 4 groups of 2. So like here's a group, and there's 2 groups inside of that group, and here's another group, and so there's a second group that each consists of 2 subgroups. And so what we have here in the end is 4 times 2 groups of cubes, and then each one of those groups consists of 3 cubes. So 4 times 2 groups of cubes, and then each group contains 3 cubes, so this is the total number of cubes. Well, here's a different expression for the total number of cubes. Those are 2 different expressions that both represent the exact same number of cubes, and so those 2 expressions should be equal. So let's take a step back and look what we did here. Both these expressions were multiplying the same 3 numbers. In this expression over here, we multiply the first 2 numbers first, and then the third number. Over here, we multiplied the last 2 numbers first, and then the first number, and in the end, we get the same result. So that's the basic idea behind this associative property of multiplication, which in generic terms says that if we take A times B times C, we can multiply the the last 2 numbers first and then the first number, or we can multiply the first 2 numbers and then the last number, and in the end we're going to get the same thing. So just like with the associative property of addition, we can interpret this as saying that we can group or associate the numbers or the factors in any way that we want, and we're going to get the same answer. So, and these properties of multiplication are very similar to the properties for addition, just that here we're using multiplication rather than addition. So that's it for this section 4.3 lesson. Your assignment before next class is to read section 4.3 from the textbook.